Okay, so we're going to be looking at Module 1, Part 2, which is going to be Chapter 4 in our book. So we're going to skip a little bit. We started with Chapter 1 doing the kinematic diagrams. And I don't know why the book does this, but this to me is a little bit more logical. And this is the order I normally teach it in. They go from Chapter 1, and then they do a little bit in Chapter 2. Chapter 3 is dedicated to vectors. And then they go back in Chapter 4 to like position and displacement of those diagrams. And I'm like, oh, we're kind of in the groove of diagrams. We've learned about diagrams. Let's kind of stay on those for a little bit. So that's what we're going to do. We're going to skip over those 2 chapters. We'll come back to 3 in our next module. But for right now, we're going to look at chapter number 4. So that's going to be what's here. So when we go in here, you're going to notice that there's a PowerPoint, and we're going to start there and then work through our chapter. So chapter 4 in our book. So if you wanted to open up to chapter 4, it starts on page 72 in our kinematics book, and it's going to be on position and displacement analysis. So as we look here, objectives wise, in this chapter, we're going to be, oopsie, I went back. I didn't want to go page. I wanted to do zoom out. There we go. In this chapter, we're going to be looking specifically at position and displacement of a point. And really the bigger focus is going to be as we move, for instance, a driver or another link in our mechanism, what happens to the other links that are, joined to it. So, so we're going to be looking at displacements in a linear fashion, if it's something like a slider that only has linear motion, or it could be in an angular fashion, something that is going to oscillate or rock instead. We're going to also find limiting positions of different mechanisms, which then equates to stroke and throw for the different types of mechanisms. And then finally, we're going to make a displacement diagram of that displacement that we find for the different mechanisms that we look at. So looking here, as we know, kinematic analysis is going to be those first steps in the design process, and sometimes referred to as layout work. So kinematics, again, is going to answer the questions like, what is the full motion of the actual mechanism that we're looking at? What is the position when we move one of the links? What happens to the rest of them? What is the extent or the range of the motion? How far is it going to go? How close is it going to be? What's that difference between the two? And then really, how much space do we need to allow for this motion so it doesn't interfere with other elements in the environment that we're designing for? Okay, that's the kinematics. So the one thing we're not worried about, or one of the things we're not worried about, is forces. Okay, so we're not going to be worried about how much force is going to be transmitted, or what the materials are, or how thick they have to be. That's not the focus yet. We're just looking at motion and spatial relationships and how things are moving.
So are we trying to look at like where they'll be like over time, like are we going to have to create like if this link moves this amount, then this part of the mechanism will move this amount?
Exactly. Yes. Especially when we start looking at a known driver, for instance, as that rotates around, if we move it, for instance, 30 degrees, then what happens to the rest of the mechanism, right?
Okay.
Yes, that's a big part of what we're doing here. Exactly. Yeah, because in chapter 1, we created the diagrams like at this point in time, right? A snapshot of where it was at. But we could see that they would, move around. Now we're looking at that movement and how that kind of affects things. Okay. So in this chapter, your homework, you're going to have dimensions. You'll be drawing to scale. You'll be kind of generating and pulling those things together and moving them around to see what their effect is from the input to the output. So the primary goal then is of positional analysis is to determine the location of points on a mechanism that are relative to other links that are going to be moving. And most specifically, most often we are concerned about, when that crank moves, what's happening to the rest of our mechanism. So displacement is the end product of motion. Now there's 2 different types of displacement that are going to be defined. And one is going to be linear, and linear just means what is the straight line motion, the difference between the furthest point to the closest point. And that displacement is simply going to be how far did we move. There we go. And then angular displacement is when we have one of those links that are oscillating and they have a fixed point. What is the angle that they move through? Okay, that's going to be what angular displacement is. So if we look at the bottom of page 73, hi, Evan. I'm going to sneak underneath here. We're going to notice that down here at the bottom of the second column, let me make this the size of my screen. This would be referred to as angular displacement. So not really knowing which is actually, it looks like the lighter link here would have been in the original position, and then it's rotated to a new position. So the difference between those two, and it's the angle between them, would be the angular displacement that occurred, during that transition. Okay. If we look at a slider, for instance, okay. And I'm gonna point to this example on page 77. We'll be looking at it a little bit more in detail. When we look at linear displacement, it's going to be when, like, a slider going in a straight line motion. What is the difference between where we had started to now where the new position is after we ended? Okay, linear displacement there, straight line. Okay. Now, in kinematics, and it's a function of a couple things. We're going to be focusing on the graphical analysis or the graphical solutions. You're going to notice in our book, it's going to always have kind of, the two approaches. It's first going to do graphical to illustrate the process, but then there's also going to be followed up with like analytical or the math that's behind it. Okay. And we're going to have, places where we're going to interject that as well, but we're going to stick on the graphical side of things. And I do that for two reasons. First of all, I think you get a lot of calculations in a lot of other classes: statics, strength of materials, design of machine elements. You're going to be doing it in your other design courses as well. And this is just a nice way to, I think, kind of come back to, making sure that we understand not only what the numbers mean after the math, but then let's also see the picture and the graphical side of it, kind of marry those two together. And then second, we only have 8 weeks. Okay. We can't do it all. So we're going to pick that one for those reasons. So we're going to be erring on the side of graphicals. So as we move through our book, you're going to notice that we're not going to take each and every one of the sections in the book. So always follow the PowerPoint presentation and always know that we're going to be on that graphical side of things, okay, drawing out the solutions for the most part. So when we look at determining displacement using the graphical method, it's going to really be about moving those diagrams that we create around. So we're always going to start with, a starting position, just like we did in chapter 1. So we're going to be identifying our frame, our crank, our connecting rod, and then whatever the output is going to be a sliding or an oscillating link most often. And most of the things that we're going to be looking at are, for the most part 4-bar mechanisms. So many times we're going to have just 1 degree of freedom. So we'll be calculating that, and we're going to be verifying that on all of our diagrams. And then we're going to be moving into determining what that displacement is going to be based on what's happening on a driver. So if we look at, and really kind of starting on page 74, we're going to see this process kind of play out. So here on page 74 in our first column, about halfway down, figure 4.5. This is our first, if you would, look at a kinematic diagram, just like what we had looked at in chapter 1. We have we have it simplified. We have our links identified with the numbers and the circles. We have each one of our joints identified with letters. Okay. And now you're going to notice that link number 2, so link that starts with A and ends with B, it's moved. Okay. Now, as we look here, and we don't really know what the machine is, but based on the way it looks, the crank is usually going to be the smallest one of our members. So, so I'm assuming that the crank is on that left-hand side there, which is link number 2, and we're moving that crank 15 degrees clockwise. Okay. And the question would be then, okay, what's happening to the rest of our mechanism here? So the first thing we're going to do is we're going to move that crank 15 degrees. Okay, so now it's in its new position. Notice that, we drew it first in its solid lines, if you would, and then its new position is going to be dotted. Then what we're going to do as we kind of move through here, we're going to go over to page 75, and we are going to look at each one of the links and what its path that it's going to take when it actually moves. So we have to look at how is it attached to, the rest of the mechanism. So as we look at link number two is anchored at point A. And it can only rotate. So it's a circular motion there. And it can only, if you would, move in an angular fashion with the fixed point at A. When we look at the other link over here, link number 4, which is considered, if you would, our output, you're going to notice it too is only going to be able to rotate about that fixed center, which is D. So when point C is going to be moving, it can only move on that curved path that is tied back to the center of rotation at D, okay? And the same thing for C. So now if B can only go on a curved path, C can only go on a curved path. Once we move B to its new position, you tell me, how do we determine where C is from this point? How would we do that? And think in terms of construction, using AutoCAD, or even construction using a compass or such. What do you think? How would we find where the new C is? So we're calling this B prime for the new position. So if we move this 15 degrees, how would we determine along that path where C would be? What would you do? What do you think?
Wouldn't you take the distance that you're traveling, like the displacement of the sine, or the sine? Oh no, I guess not. It's
graphical. Think graphical. Don't, you know what? And I'm not saying that the math isn't really good, but think graphical. I want you to think about how you would draw this out. Don't worry about the math right now. You can check it with the math, but let's see how we would draw this out. Any ideas on that?
So from B prime, it would be the same distance using number 3.
Yes. This is
intersects the
exactly. So this is the length from B to C, and that's a rigid length that's going to remain the same length throughout, the whole linkage path. So now we're going to take that length and we're going to go like this, and we're going to strike an arc and see where it intersects the path that C took. Okay, that's exactly what we're going to do. Okay, so now if we turn the page, that's what we see right there. Okay, so now we took that distance, that radius of B to C, or the radius of link number 3, and we're going to strike that arc. And now that will be the new position, C prime. And we would draw a line simply from there to there. Okay, I wish they would finish this problem in here, but they don't, which is kind of silly, but that's the construction of it. So that's the graphical work that we're going to be doing. Okay, all right. So we're going to be drawing this out using AutoCAD. Now, you could use scales and protractors to do this work as well, but unfortunately, it's just not going to be as accurate. Okay, so when we have tools like AutoCAD that we can utilize for this, then it just seems to make sense to do that. Okay, so that's really why we're using the tool. Now, when we do our drawings and we do our work here, the graphical solutions in AutoCAD, I just want to let you know we aren't being super perfect like we do when we create a drawing to send out to be produced on the shop floor. Okay, we don't have to worry about perfect dimensioning schemes, and there's not standards for how that's going to look. It's more, we just want to prove the work, lay it out so that as we're pulling everything together, we can make sure that everything fits. Okay, so that's the sense that we're using these diagrams for. Okay, let me catch myself up in my PowerPoint and see where we're at. So you'll notice here we do the kinematic diagram. I didn't point out, we always do check those degrees of freedom. So we want to make sure for that. Then we want to move that driver to the desired position. That was the 15 degrees for this particular one that we were looking at. And then you want to displace the remaining, they call them slave links, meaning those are the ones that are connected and they're dependent on that driver for their motion. Okay. So let's look at example 4.1, and we're going to be looking at these examples and we're looking at them in the book just so that we can see the process that we go through. And then I want you to be kind of thinking about how this would play out if you would in AutoCAD, for instance, as you're creating these graphical solutions. So let's look at problem 4.1. This is on page 76 in our book. And these examples, as we look, I'll be kind of pointing out, they'll kind of be your guide to what you'll be handing in for your homework problems, but we'll come back to that when we kind of get ready to look at that. So here you're going to notice we have a mechanism right down here. It's referring to figure 411. So we actually have, in this case, 6 links. Okay, our slider is our 6th link here, and it has everything identified for us. We've got the frame. Actually 2 connections to the frame, and then the slider is relative to the frame. But then we've got link number 2, which is going to be our driver. We're going to find out link number 3, 4, 5, and then that slider is number 6. Okay. And first things what we want to do is we want to find out, we want to graphically reposition the link so that link number 2 is displaced 30 degrees counterclockwise from where it's at. So as we look here, link number 2 is right there, and we're going to move it counterclockwise 30 degrees. Okay. Counterclockwise 30 degrees. Why are we clicking? I was just curious. Are you doing the homework already? Don't do that. Don't do that. Okay. I'm going to give you a little lecture. I'm going to be the naggy teacher right now. So, and I'm going to give you a really good example. So last night I was working in, I was doing a couple doors down. I was doing 3D parametric. It's Creo. It's the first class is in Creo. And as you know, Creo is, I mean, it's complicated, right? And I totally understand, and I totally get it. Students are excited to get on the 3D software, so they start, going around. And I tell students, I don't mind if you try to follow along with me. It's totally good, totally great. But if you start falling behind, and my expectation is I'm not telling you what buttons to push, I'm just giving a demonstration of what we're going to be doing. And you'll have plenty of time to work on it. But everybody want to jump to the homework to get that done, right? And so I had one particular gentleman, and I had gone through actually numerous times, and the examples that we did, I'd walk through how we start the files, what we go into, how we save them. And I mean, I must have done it 5 times. And by the time we got to the second night, it must have been about 10 times, honestly, because I go over that each time. So then he asked me to come over, and I'm looking at what he did, and I can tell right away. He's like, how come I can't pull my drawing up? You didn't save it. Oh, I didn't know that. I'm like, yeah, because you got your earbuds in, listen to music, you're fooling around, you're not paying attention. And now we had to start over everything. He's like, oh, then I got to do that for all of these. I'm like, yeah, you do. Oh, I didn't know that. Do I have to do that? Yeah, you do. And I felt bad saying that because yeah, it's kind of a pain in the butt, especially when it's Creo, right? Now I gotta do all that again. I'm like, oh, good thing it'll be quicker the second time around. But if you jump to all that, you really could be wasting time. You're going to be less efficient because I'm gonna kind of clue you in on the stuff you need to do and maybe don't do. Okay. So please, while we're doing the demonstrations and I'm going over things, and especially, I mean, I understand if we're in AutoCAD and you want to kind of follow along, that's fine. But yeah, don't be worrying about the homework just yet. There's plenty of time. I know it's Friday night. I know you want to get it done, but it's not due till next week. So don't worry about it. Okay. So yeah, just be patient with me with this. Okay. I promise it'll always be worth your while. It might not be the most exciting thing to be listening to, but I promise you, it's always getting you to what I need you to do. Okay. So enough of that. So as we look at this process here, we're going to be moving this in a counterclockwise direction, 30 degrees. Okay. And then what we're going to find out is, okay, when I move that driver 30 degrees counterclockwise, how are the rest of those other links? How are they going to be repositioned? And ultimately our output is right here on our slider. How is that going to move? Okay. How far is that going to go from the position that it's at right now? So job number 1, kinematic diagram. Job number 2, recheck and make sure that your mobility is what you expect it to be. A lot of times you can look at these kinematic diagrams and you're going to notice, yeah, I can see how that's going to work. Then confirm, is it only one thing that I have to move in order to get this to go? And you should see it. And if you don't come out with the number one, you may have forgotten to label a link or a joint, and you want to go back and just double check that. So always do that. Okay, that's good practice. Now that we have this in place, now we're going to do that movement of. So we're going to go up here. Now, again, I know I don't know. I tend to stay away from demonstrating the AutoCAD so much because I think sometimes it can take me longer to kind of go through it than to look at these. So always look at these in terms of how am I going to construct that in AutoCAD? And you all have that experience in your past, and we've gotten that practice so far in chapter 1. So so as we're looking here, you're going to notice that we're going to now rotate that link number 2 counterclockwise, that 30 degrees. So you're thinking, okay, I can just simply rotate that in AutoCAD, right? You know, you just rotate that link, do a rotate copy so that you leave that other one behind. And then now what I need to do is I need to see how the rest of the links are going to move relative to it. So before I even worry about where the next one is going to end, I really need to determine what is the path of anything that's going to move. So you'll notice here that we have our hidden lines. This is going to move only along this arc that is going to be centered at point D, and it's going to go, you know, around along that. Now, in AutoCAD, where you're probably going to tend to do is you're probably going to draw circles. I'm sorry, I just noticed there's a chat here. Let me check. Did my camera freeze or not? I don't. Oh, I think it might have. Evan, you look frozen.
Yeah.
Right now.
Evan's camera froze.
That's you're able to see me and it's working okay for you though. You can hear and see me fine. Yeah, you're concentrating really hard. You are not clicking. He is focused. Yeah, I can see and hear you perfectly. Okay, then we're good. Yeah, no problem. All right.
I actually had a question.
Yeah.
So when we're doing that in AutoCAD, drawing the circles, we're drawing it, the radius is the length of the linkage to the point that we want it to be.
Yep.
Essentially we're layering it so it's a hidden line to kind of give us a reference of where we're
that is going to be your choice, how you want to, and it's great that you brought that up because I do mention that all the time. How you want to manage these lines is totally up to you. You'll notice that here in this illustration, they did do hidden lines, right? And if you find that to be what you want to use, great. That's beyond the kinematic diagram. I don't worry about, you know, setting up standards for you. Some students like to use different line types. Some students like to use different colors. You can go that route too. So, so whatever you want to use to kind of show the difference between, if you would, your befores and afters or the paths that things are going to take, I'm going to let you decide that. Because then when you take your screenshot, because you'll be taking it of a color screen and you'll be, you know, putting it in a document or just saving or just uploading it, I can see those colors too. So, so however you want to differentiate, but I wouldn't do all, you know, one line type. So for instance, I wouldn't do kind of like what they did. You can see a little bit of the gray to the black, but I think there could be a better contrast. I would have probably done, if I'm going to do something monochrome, probably done line types or line widths would be another way to get at it. But yeah, use the power of the CAD to make those differences, but that'll be a personal choice of yours. So before we get down here, so those are the paths. So once we have our paths marked off, now what we can do is then strike the next radiuses. So we're going to start then where we moved our link to. So at the endpoint of B here, we're going to take that radius from B to C that we had originally, and we're going to strike that arc. And then we're going to take the connection from C to E, which is link number 3, and we're going to strike that arc. Okay. And then we're going to draw in the new positions of each one of those links, kind of like connect the dots, if you would. Okay. And then you're going to notice down here is then the result of. So this would be, you know, what you would end up with. You would show the two views, the before and the after. Now they also differentiated by putting primes. So they still had their same joint labels here, A, B, and C, but their new one is like B prime, C prime, and E prime, okay, to the new motion or to the new placement. Now, you also have to add dimensions to answer the questions that were in the problem. So as we look back over here to the beginning of our problem statement, it says we want to know what the resulting angular displacement of link 4 is. Okay, link 4 is this link right here, the angular displacement. And then we want to know what the linear displacement is of point E, which is the center of our slider. So those two dimensions have to be identified in your solution. Okay, so over here, you'll see that they have 30, well, that was the original 30 degrees, sorry, 26 degrees here. And then they have the 0.9544, okay, is going to be that dimension. So I would be looking for AutoCAD dimensions answering those questions. Okay, does that make sense? And again, besides, you know, the standard kinematic symbology that we did, you know, that we practiced in chapter 1, how you want to show that second phase is totally up to you. Okay. All right. I know it doesn't look like it's going to be fun.
Actually, is there any preferred method? I guess what I'm asking is like, so we can use either different colors or hidden lines as long as it's visible and it's
Yeah.
like, it's clear to see what
Correct.
is happening. It's okay.
Mm-hmm, mm-hmm.
Okay. I just wanted to
Yeah,
clear.
I don't want to dictate everything.
I-
And it's
I
kind
just-
of it's kind of nice
yeah.
seeing how other people do it. So truly, yeah, I like I said, whatever your preference is, if you want to change line types, you're going to be creating different layers for each one of these that are going to, whether it's different colors on continuous lines or if it's different line types and different colors, it's totally up to you. It's totally up to you. Mm-hmm. Okay. All right.
Okay.
And always just keep in mind as well that this is used for layout purposes. All right. So you don't have to have the perfect height dimensions. You don't have to have the perfect hood notes and the balloons and all that kind of stuff where because once it's laid out, well, then you're going to start doing the details beyond that for the individual parts. And that's, you know, when you start releasing those and getting those in their final form, that's when you start, you know, applying the standards and putting things on drawings and stuff. Okay. But not here. This is stripped down, simplified layout work.
Okay. I actually have one more. I have one more question.
Yeah.
So I'm looking at the examples for that part, and I'm not seeing like linkage numbers laid out. I see that like there's different like commas or the
Yeah, they have the primes next to the numbers. Yeah.
primes next to the numbers.
You know, that's great that you identified that because what I would be looking for is at the very least on your initial one, I would want to see the 1, 2, 3s, and 4s. Yeah. Yeah. Keep those. You
Okay.
want to have your link numbers. And then when you do your moves, you don't have to do that because it'll start getting kind of cluttered otherwise to do, you know, 2 1s, 2 3s, 2, you know, and so on.
But do you want
I would want to see, like, for instance, a 2, a 1, a 3, a 4. I should, oh, here, no, I got off. Sorry. This was my 3.
But would you like the linkage points labeled as well on the moves?
No, I wouldn't.
No,
I wouldn't. I
okay.
think it's going to get too cluttered with that, just on the initial one.
Okay, I just wanted to clarify just so
Yeah,
that.
no, I'm glad you asked that because yeah, they didn't put that in here. Yeah, we want to continue to do that. Okay, good. Good. Any other questions? All right. Let's go back to our PowerPoint and see where we're at. Okay, I think we're doing another example. Yes. So we'll turn the page. We'll look at another example. This is going to be example 4.2. So very similar type of problem, but a different mechanism. Okay, so here we have a compound lever snips. It's shown in our illustration. They're often used to place in place of regular tin snips when there's large cutting forces that are required. Using the top handle. So here's the top handle, which is connected. It's all one piece and it actually goes to the bottom here. Do you see that? It's all one piece right there. That is going to be identified as the frame. They want you to graphically reposition the components of the snip when the jaw is opened 15 degrees. So where it's at right now, okay, so this is the top jaw. Okay, this is going to be part of what we're going to be interested in moving, okay? we want that to go, if you would, 15 degrees up that way, okay? We want to open that up 15 degrees. What is going to be then the displacement on the lower handle? So the lower handle is down here. It's kind of like equating to like, how far would I have to open up my hand, right? To actually get it to that 15-degree opening on the jaw side, okay? And this is really a very practical problem, especially when we're looking at something that, you know, somebody has to use and be able to do like with their hand, right? So, so first things first, draw the kinematic diagram. I'm not going to have you guys do that because again, I kind of want to get through the material here tonight, and not that that's, you know, not worth the time, but time is of the essence in an eight-week class, right? So, so we're going to peek over here to, you know, at the top here. Here is our kinematic diagram, okay? And this is going to be that bottom handle. This would be the top handle in here, okay? Where that loop is for the fingers. Over here is going to be the, that's going to be the top jaw in its closed position. So that point X is point X like right here. So this kind of comes over the top. Here's that going to be point A. And then this is X for where that's in its closed position, okay? Now what we're going to do is we're going to take that and we're going to rotate it. I'm sorry. Yeah, no, I'm sorry. The gray now is the new one. We're going to take that and we're going to rotate it open. So it's going to stand open 15 degrees, okay? And that's going to rotate about this point right here. And the 15 degrees translates down here as well. So when it's open, then what we want to do is we want to reconnect back to that lower handle, and we want to rotate it to see how far, you know, what is the angular displacement then of that handle, to find out if that's reasonable for how far you'd have to pull your fingers apart to get that to happen, right? So, so as you look here, you'll notice that they marked off their path for each one of the points that's connected back to, you know, this this link number 1, okay? So by doing that, then you'll notice that I'm going to go down here, rotating around point D here, then this handle is going to go down to open up to that 15 degrees, and it has to open up 34.4 degrees, okay? So measuring that final angle. So this was, if you would, the final result that we wanted, but then we wanted to know, okay, to do that, what's the work that has to happen, or what is the angle that has to be achieved in order to get that 15 degrees, and it needs to be 34.4 degrees, okay? Now, couple things that you'll notice here. In this case, they actually did hatching for theirs. That's up to you. You know, you don't have to. You can leave them open without the hatching on the inside, okay? And then you'll notice that they have all of the points identified, but again, they skimped on putting the numbers of each one of the links. Add it, please, for that initial diagram, but then you don't have to add it for anything that you move, okay? And then you'll notice that they have the dimension for the 15 degrees, but then ultimately we also need a dimension for the output or the angular displacement that occurred for answering the question. Now, in this case, it's nice to have the drawing here, right? And you've got the 34.4 degrees. You can maybe go like this. Can I open 34.4 degrees? I don't know. Okay, it might be kind of hard. What would the next step be? So this was the layout work, okay? So here's our you know, our hand tool. Here's our layout work. What would maybe be the next step in the design process as we look at this? Ship it, make it, ship it, done. I don't know. Even before that, even you're gonna do that for sure. You're gonna determine what is the force, what are the, you know, is it reasonable maybe for a, you know, regular size adult hand to do that work, or is it, you know, openable, but, or closable if you would. But even before that, before forces, before materials, what would we do after we got this? Okay, we think it's going to open 34 degrees. This is what we want. We think things should look like. But what do we do next?
we would model it. We would try to
Yes.
like actually model the item with the actual dimensions in like a 3D model or and simulate the displacement.
Yes, you could simulate it on a computer. If you made a model, what else could you make? If you made a 3D model, what else could you make? Like a
Your
3D, like parametric
like
model. What
like
could you do then?
your assembly.
You
Oh,
could
oh, you
make your
could
assembly, yep. And then what could you do after you make your assembly?
couldn't you do a force analysis or you
No,
could
no,
also
no, 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 no. Before the force analysis, we already talked about that. Remember, kinematics is not, we're not worried about the forces.
uh you can animate it
You
and
could animate it, yep, on a computer, absolutely. But maybe I want to like hold it. we could some way somehow prototype it. Maybe that is 3D printing it. Maybe that's, you know, cutting out some, you know, maybe we have an existing one that we could maybe you know, do some adjustments to. But what you probably want to do at this point is kind of get your hands on it and see, is that reasonable? And there's, you know, and there's no other, you know, really perfect way to do it than to actually make one that we think it's going to look like. And if 3D printing is that mode to do that, it might be, or it might be a couple of things, but some way, somehow prototype it. And then after that, if that all looks good, if the motion looks good, if it feels good, now let's start looking at forces. Let's start looking at materials. Let's start looking at how are we going to produce this, you know, in a you know, a large scale factor. Okay. Yeah. Think of what your mouse. Okay. Mine isn't even really a super fancy mouse, but it's kind of ergonomic, right? It's kind of ergonomic. The one that's over here on the desk, this one's not. Okay. Some people prefer all different types, right? If you're a gamer, they can be like super fancy, right? They're like space mice or something. I don't know. But to get these mice to be more ergonomic, what do you think they did? Some kinematic analysis first, right? Before we worried about, you know, the thicknesses and the types of materials and maybe even the padding that's along the side. First, you had to get like the contours and see, is this going to hold nice in a hand? Are people going to like it? Then you may even have a number of people test it out and try it and see which style is their favorite. Okay. And that's really what something like this you could do too. And in any sort of design phase, your layout work, your kinematics, this is where you're kind of testing out that motion before we're even worried about any of like the other, if you would, hardcore stuff. Okay, getting it to its final form. All right. This is so good, right? Okay, stay awake, people. It's Friday, it's late. Okay, let's get back to our PowerPoint and power through. Okay. Limiting positions. Okay, one thing to just move things and just like, you know, say, oh, I'm going to move this 30 degrees. But a lot of times we want to know, what is that furthest place away and what is that closest place, so if that output is going to be. So for instance, if I've got a piston, I want to know what the stroke of that piston is, right? And that stroke of that piston is, how far is it going to go? How close is it going to go? What's the difference between those two? What's the total? I'm going to go here. What's the total travel of that output? Okay. If I'm looking at something that's oscillating or rocking, I'm going to be looking at the throw of it. So stroke is going to be like a linear distance, total distance that something travels, but a throw is going to be, oh, what's the total angular displacement does that have? Okay. So limiting positions is finding those places where the other links are going to be positioned so that we can get that output on its extreme furthest out and extreme closest, whether that's linear or angular. So if we look at figure 425, so we're skipping a bunch of pages here. We're going to look at figure 425, figure 425 up on the top of page 88. Okay, on the top of page 88 here, they have both examples. In the case of a crank slider mechanism, the stroke is going to be the difference between the furthest out position and the closest position as the crank goes around its full circle. Okay, as the crank goes around the full circle, we call that a cycle, a full cycle. Okay, and then the difference between those two is called the full stroke. That's the full displacement that we're going to have. When we have for instance, a 4-bar mechanism that's going to be a like a crank, what do we call it? A crank rocker. okay? That means that our crank is going to go around a full cycle 360 degrees, but then our output is going to oscillate going back and forth. It's not going to go around a full 360 degrees. So we want to know what is its maximum amount of angular displacement. So what is the difference between this one and this one? The internal angle there that's going to cover. That's called the throw of something that's going to oscillate. You maybe have heard that before. Okay. All
So
right.
so we're only taking the angular displacement of the of the one linkage, not the total system.
Correct.
Okay.
Correct. Yes, it's going to be the one link. Like, and we usually consider it, most often we consider it like, we call it like the output. Okay. Because this is going to be our input to kind of like get that motion going. And the end of our mechanism is our output. So what is that output doing? What is its angular displacement?
Okay.
Yep. Okay. So I think we're going to be looking at problem number 4-6. Problem number 4-6. So problem number 4-6, let's read the problem statement, and then we're going to be going through all the steps here. So we have a mechanism. It's driving the linkage of a reciprocating saber saw. Okay. We want to determine the configurations of the mechanism that places that blade in its limiting positions. Okay. So it places that blade its furthest part down and it's closest up. Okay. So what is the stroke that's going to be accomplished then? Okay. So as we look back at our PowerPoint presentation, got a couple things to consider here. So first and foremost, we're going to do our kinematic diagram and determine the mobility, just like we have been doing, all the way along. And we're going to do it in the position that we're seeing it here. We'll see that in an example. Next, what we're going to do is we're going to calculate the furthest extreme position, FEP, and the nearest extreme position, the NEP. Now, to do that, we're going to take the lengths of link number 2 and link number 3. So this is where you're going to start probably settling in on, okay, my input or my crank is going to be link number 2. My connecting rod is going to be link number 3. And then my output, whether it's a slider or a reciprocating type of a link, it's going to be link number 4, because that'll be my output. So kind of using that system, we're going to have the length of link number 2, which is our crank, plus the length of link number 3, which is going to be that connecting rod. And that means that they are in line with each other, like in their furthest extended positions. Okay. And that's going to be the radius that we're going to use for the furthest extreme position. Then what we're going to do is, as that rotates around, that crank rotates around, the link number 2 is going to like overlap on 3. So we're going to take the total length of 3 and we're going to subtract off the length of 2. And now that's going to be its closest or its nearest extreme position. And we'll see how this plays out. It makes more sense when we see the actual graphics of it. Then we're going to strike our arcs for those centers across where, in this case, our slider travel is going to be. And then that's going to mark the highest and the lowest positions. And then we're going to draw it in those 2 positions. And then we're going to dimension, we're going to dimension the distances and or angles, depending on the type of mechanism. So as we look here, using that process and kind of referring back to those equations when needed, here's our reciprocating saber saw. So here's our motor going to be going around, okay? The connecting rod is connected to this, if you would, what I believe to be like a flywheel. Okay, I'm not exactly sure if it's used in that sense, but it's going to be from the center of our motor rotation to, and this is just going to be a simple, we're going to see it as a simple radius to where it connects to that joint on our connecting rod. Okay, this is going to be our crank and it's going to rotate around. Now that's going to then connect to our slider that is going to be constrained to be in a vertical linear path. Okay. And then the saw is actually connected to that, the blade itself. Okay. So we want to know what is the furthest down position that this is going to go for that slider, and what is the closest up along that line of action. Okay. So over here, first things first, kinematic diagram, right? So here's our kinematic diagram for that 4-bar crank slider mechanism. So here is the motor. Here is that radius connecting to the connecting rod. And then here is going to be the slider going up and down. And then, you know, essentially the blade is going to be down here. Okay. Now, mobility equation, I think they did it somewhere along here. They might not have, they should have. It is 1. We can see that it's 4. It's going to be 4 minus 1 times 3, right? And then 4 times 2. So it'll be a 1. But make sure that you get it in there. They did not illustrate that here, unfortunately. But then what we're going to do is, as we look now to get those extremes, let's remember what our equations are. So for the furthest out, we're going to take the length of link number 2 plus the length of link number 3. That's when they're in line with one another. So if we go over here, we're going to take the length of link 2 and the length of link 3. Going back to the original illustration, these are to scale this time. So we have a 1/2 inch is the length of link number 2, that little radius. And then the length of link number 3 is 1.75. So when those two are straight in line with one another, that's when they're going to be their longest added together. So over here, you're going to notice that from the center of rotation, here is the radius that's equal to the length of L2 plus L1. And they strike that arc, and where it is going to intersect with the vertical path of our slider is going to be its most down position of point C in this case. Then we're going to rotate this so that this is going to go in the back side. It's going to be in line with link number 3. So that means we're going to take link number 3 minus link number 2. Okay. Pointing at the air, if you would. And then we're going to take that radius and we're going to strike the arc to be in its upmost position. Okay. And then we're just going to put it in the limiting positions. And then the difference between that highest and that lowest value is going to be our stroke. So in this case, when we have limiting positions, we have actually 3 positions of our mechanism. We're going to draw it in that original place. Then we're going to draw it in its furthest down in line place. And then in its upper place, its highest position. Okay. And again, they did not put the link identifiers on here. You want to at least do that for the initial mechanism. Okay. And then solving the problem, answering the question, here is the length of that stroke, the difference between the lowest and the highest position here on that slider. Any questions? Okay. All right. I think we have another example just after this. Yep. 4-7. 4-7 is the same type of limiting position problem, but this time it's going to be a crank rocker 4-bar mechanism. But the same equations are going to hold. It's just that when we cross a path, instead of it being a linear displacement, this is going to be an angular displacement because it's a rocker on the output. So let's look at the problem. On page 90, at the top, we're going to see problem 4-7. And this illustration is for the operation of a water nozzle for an automatic car wash. We want to determine in the limiting positions of the mechanism that places that nozzle in its extreme position. So the nozzle is here, okay? And here's the connecting rod, the crank, and then here's the motor, okay? So as this motor goes around and around and around, this connecting rod is going to move up and down, right? And then this nozzle is going to oscillate on this center right here, and it's going to go like that, right? And it's going to kind of sweep, if you would. And it's going to then spray out the water in a car wash. Okay. So we want to know what is the resulting highest position angularly of that link number 4, what's going to be link number 4, and then what is the lowest so that we know what the total throw is of that nozzle. Okay. And then we can see, is it going to be something that's going to provide the coverage, right, that we need for our car wash. Okay. So step number 1 is going to be determine or put our kinematic diagram in place. Okay. And that's going to be down here. So right here, we have a standard 4-bar mechanism. Here's our motor, the center of our motor, our crank, connecting rod, link number 3. And then link number 4 is going to be that nozzle. The nozzle is, out here a little bit. If you wanted to add an extra point of interest, you certainly could. I think that would be called for, but in this case, they didn't. And then they're going to do that very same construction to find the furthest extreme position. They're going to add these two together so that they're in line with one another. So you'll notice here that they're going to find that radius by adding those two lengths together of each one of those lengths, and then striking the arc, and then it's going to intersect with the travel of that arc C, or that arc for point C. And then we're going to take for the nearest extreme position, we're going to take that link number 3 length minus link number 2. We've got a shorter radius this time from A, and now that's going to intersect with the travel of C for its, highest up position. Okay. And then we're going to draw it, and then label or dimension that angle. So here you'll notice, in the wrong direction. There we go. Here you'll notice we have the original position, okay? Then we've got it in its extreme position all the way down. That's where link number 2, link number 3 are in line with one another, okay? And then in the position all the way up, this is where like link number 3 overlaps link number 2, okay? And then that's going to be its position in its highest position. So the total throw looks like it's going to be 47 degrees, okay? Not inches. So in a case like this, because we have an oscillating length, it's going to be angular displacement we're interested in, not linear. We're not looking at how far this is open. We want to know the angle from, where it started and where it ended, okay? When we have a slider, that's going to be linear distance, okay? All right, questions? Okay. Besides, when is this going to be done? On a Friday night. A Friday night. So good. You guys are dedicated. I love it. All right. One more section to go over, and this is displacement diagrams. So displacement diagrams are going to give us a graphical plot of what the displacement is of a mechanism, okay? And it's going to be relative to driver or crank angle, okay? So we're going to be creating a plot, X and a Y, and the X-axis is going to have the driver displacement on it in degrees, and the Y plot is going to have the follower displacement in inches or millimeters, whatever the distance might be, okay? Now, I am going to go to, let's see here, page number 99, and that's going to be the example we look at. So on page 99, actually, I'll start at the bottom here. This is example 411. And this is a driving mechanism for a reciprocating compressor. And we want to plot a displacement diagram of the piston displacement relative to that crankshaft motion. So let's look at the actual mechanism itself and then the kinematic diagram. So I'm doing it like that. So here is the actual mechanism. So we've got a crankshaft, okay? And we've got our crank, which is going to go around. Connecting rod goes up to the piston, which is in the cylinder. So the cylinder holds that piston or constrains it to vertical motion. So as our crank rotates, it's going to pull that piston down and back up and down and back up and so on, okay? And what we want to do is we want to plot for every 30 degrees. If I move my crank 30 degrees, what is the displacement from top dead center? Is that going to come down? Okay, and then I'm going to move it another 30 degrees. What is that displacement from top dead center to the new position? And then the next position, and so on, as we increment in 30-degree increments around a full 360 degrees, okay? So to plot that, the displacement diagram is going to look like this, okay? It's going to look like this. So as we see here, our x-axis, as it's stated, is going to be our crank angle. So this is going to be going from 0 to 360 degrees. And you'll notice that this plot is in 60-degree increments, but the more points that you get as you go around, as you can imagine, you're going to have a more accurate graph and a curve to actually put on here. okay? The vertical axis is going to be the piston displacement. So this is going to be our distance. This is going to be inches or millimeters, whatever it might be, okay? In this case, it's inches. Now, imagine this is our 0, 0 down here. So this is top dead center right here, okay? So it's kind of like backwards, if you would. So it's when the piston is in its highest position, because then each time we rotate that crank, this is going to go down. And we're gonna find that distance from there. So this is like our, I'm gonna say this is our 0. And every time we rotate this crank, this is gonna come down an increment, and that is gonna be our displacement, okay? And then we're gonna go down again, and then we're gonna have a new displacement, and we're gonna still measure all the time from 0. That's gonna be our, that's gonna be our displacement there. Can't see it because it's pencil, okay? Always measuring from that top dead center, not the distance between the points as it goes. It's always going to be a reference back to, if you would, that start point or that 0. Okay. All right. So you'll notice that the first thing they did was they drew a kinematic diagram in its simplified form. You guys will do this as well for whatever, for the one that you're going to do. And then you are going to rotate your crank 30 degrees. And what's going to happen is this is going to go into its new position, right? And then this is going to come down a little bit, and we're going to have a new place. And what you're going to do is you're going to measure from that position to the new position, and that's going to be the corresponding displacement. So if you moved it 30 degrees, your distance from top dead center to its new position now is going to be this distance. And then you're going to plot that, okay? And then you're going to move it another 30 degrees. You're going to find the 60, and you're going to find out, oh, what was that displacement? And that's what this graph does for us. Okay. Now, nobody in here had me for computer programming, right? Because I wasn't here when you guys had computer programming. But I believe you guys created a displacement diagram in that class. Correct me if I'm wrong. Do you guys remember doing that? It was so long ago. And even though it was long ago, let's look at something.
Yeah,
So,
we created one in there.
you created one, yeah. So and I think it's gonna benefit you because I did it for, let me see. I'm gonna go back to module number 2. Okay. We're going to look at 2 things. You're going to notice that there is an Excel spreadsheet in here, and it says assignment 4. Don't worry about that. That was what I called the assignment. That was when we did. That was assignment 4 in that computer programming, and I just downloaded the file here. But this is an inline slider crank mechanism spreadsheet. Oh, shoots. I didn't want to do that. I'm sorry. I don't want to look at it. I want to actually pull it up. And now in this slider mechanism, you're going to notice that, oh, this is the wrong one. I'm sorry. Wrong one. I was playing with it. I want my inline, not my offset, inline. Okay. So here is the displacement diagram that we have here. So it looks similar to the one that we saw earlier, right? Okay. And you're going to notice that the crank angle along here, this is 360 degrees. I'll just wait for you guys to be done.
I'm trying to pull up this.
I'm going to just show it to you right now. It's a regular spreadsheet. It's nothing super complicated, honestly. I want to show you how it works, and I want to show you the elements here, how it's similar to what we have here. So you're going to notice here that we have 360 degrees along our x-axis. And then we're going to have our displacement in inches going up. Okay. Now over on the left-hand side here, the tables that we have, this is an inline crank. Okay. Crank slider mechanism. I don't have one for an offset. You will do an offset. And I think you guys created the offset one. So, so you'll have both if you want to use them. But in this case, here's my crank angle. I move this every 5 degrees, even though the assignment that I have for you, I want you to check it every 30 degrees, but the spreadsheet does every 5, just so that the graph is more accurate, and you can put as many points in as you want. But how this works is L2 is going to correspond to the length of link number 2, or your crank. Okay. And then L3 is going to correspond to the length of link number 3. Okay. So those are the two links that we've been kind of dealing with when we go, you know, furthest extension point and then the nearest. So for instance, for this example, the length of our crank is 0.75, okay? And the length of our connecting rod is 2 inches, okay? So now what you're going to notice is it updates everything in our spreadsheet. It updated our graph, and you'll notice that now, although we don't read it, the high point, the stroke of it is 1.5 inches. And you're going to notice here, when you compare it back to the diagram they have on the book, it matches that exactly, okay? So you are going to be doing an inline slider crank mechanism, and you're going to plug your numbers in here, but that's not going to get you 10 points, okay? So, so to finish up that problem, what I want you to do is I want you to graphically position yours in a couple different places so that it kind of proves the numbers that you see here. And I want to make sure that you understand what you're getting from this spreadsheet, okay? So, so let's look at the homework problems, and this will kind of make a little bit more sense, and we'll kind of start at the bottom and move our way up. So I'm going to go back to module number 1, assignment 2. Okay, assignment number 2. So we're going to start at the bottom of that assignment. There are 2 problems. These are your two displacement diagrams that you're going to do. So for 470, this is worth 15 points. This is the slider crank mechanism that I just showed you, and this is an inline. So if we look at our book at the end of the chapter, this pertains to problem 5-6, okay? And then also 70. You'll notice that 70 is here. And so when we look at this mechanism, this is a crank slider mechanism where the same inline position from our crank is in line with the piston center as well. Okay, so it's that same form on the spreadsheet as it was in that last example. Okay, so what you're going to do is you're going to, use this as your calculator. Okay, so you can use the Excel spreadsheet that I have made for you. You don't have to create it or make one like it. You can use that one that's there, just download it. But if we go back over here, what you're going to do is you are going to prove your answers for 30 degrees, 60, 90, 120, 150, and 180. Okay, so 1/2 every 30 degrees. I want you to determine what that displacement is. I want you to draw this out. Use the graphical method to do that. Now, what does that look like? I'm going to show you. So if we go back to module 2, part 2, and we look at this handout right here, inline crank slider model. Okay. All right. Now, I'm gonna make a disclaimer here for you. You don't have to do all these levels or all these labels at each point, okay? But what you will do is you're going to show yours in its fully extended position, which in your case will actually be horizontal, okay? Then what you're going to do, that's going to be your furthest out position. Then you're going to move your crank, however many degrees it is. So I think, well, for ours, it's 30 degrees. You're going to rotate it 30 degrees. You're going to then mark off how far did your slider come down, okay? And this displacement, this delta from that top dead center down is going to be the number that should match your spreadsheets at 30 degrees, okay? Then you're going to move it to 60. That number should match your spreadsheet, okay? And so on, all right? You're going to do it every 30 degrees to 180 because an inline slider crank is the mirror image on the other side. That's why. Okay. All right. Now you have that spreadsheet. So I want you to put your numbers in, get your numbers, and then just prove these first ones. Now, labels wise, what does this look like? You don't have to make it. I mean, I'm not going to say mine's perfect. I don't think it's perfect, but you don't have to go to this degree. If you wanted to move it and just have, if you would, lined here and you just have a crossing point and you have your dimensions, I'm totally fine with it. You don't have to like redraw the slider down and all of the joints and then relabel all that kind of stuff. No. It's layout work, okay? And I don't want you to spend hours and hours and hours on this. Just mark off your distances and make sure that they're matching what your spreadsheet says, okay? If you just do the arcs, that's perfectly fine. But then like dimension wise, say like, I don't know, 30 degrees or whatever, you know, some way, somehow. So it's obvious that this one is for 30 degrees. This one is for 60. And if you just do the arcs and then the measurements, that's totally fine with me. Okay.
You wanna know the difference between the connecting rod and like the angle, like.
Nope. I needed that when I taught this in computer programming so that we could program the spreadsheet. That's why those are in there. Okay. But for graphical method, we don't need that. But I want you to tie your graphical method to see how this is done over here on the Excel side. Okay. Now, if you kept your stuff from your class, okay, or if you're really good friends with somebody who did, you guys made an offset one. So let's look at the next one that you have. Okay. So, oopsie, I'm sorry. If we go back and we look at assignment number 2 and we look at number 71. Okay. So number 71 is going to be the displacement diagram for problem number 4.7. So here is problem number 4.7 at the top of page 102. Okay. This is an offset crank slider because this time I don't have my my crank in line with my slider. It's offset in this case by 1/2 inch. Okay. So my calculator doesn't work for this one. Yours does, if you have it yet. Does anybody know if they have it for sure? I think Logan thought he had his. Someone in my earlier class thought they had it. They can dig it up somewhere, right?
No, I absolutely have mine. I just saw it
Logan
yesterday.
has his. Okay. All right. Yeah. So feel free to use that. Now that one, because it is an offset, is not a mirror image on the 180 degrees, unfortunately. So you do need to, what I want you to do on this problem is I do want you to do it every 30 degrees all the way around. But again, simplified versions of, you don't have to draw the full kinematic diagram for each one of those 30 degrees. Just move, move and get your distances off of there. Okay. All right. If you have the spreadsheet, that's great. It says no spreadsheet is necessary. So if you can't find it, don't spend hours trying to make it work or feel like you have to find it. If you happen to find it, great. And you can kind of check your answers. Otherwise, just do the manual calculations and that's it. If you wanted to chart it in Excel, go ahead. Or if this really isn't hard to even do in AutoCAD, quite honestly, because when we look at how we would chart it, it's just making the points. You can go along the line and then do a spline through the points. I mean, that's another way to do it too. So if you can do this all on AutoCAD if you want to, but I know you guys have like Excel experts, whizzes, right? So those are the last 2 problems. Any questions just at the moment on those? Okay. All right. Now let's kind of start at the beginning of the assignment. And I think you'll kind of see what we've got. Now it looks like a lot of problems again, right? But if you remember from chapter 1, you're going to find that some of them are clumped together with the same kinematic diagram. So let's see how that works out. So we're going to start at on page 101, and this is going to be 4 and 5 or 5 and 4, 5 and 4, 6. So going back to that illustration, you're going to start at the beginning of the assignment, and you're going to draw the kinematic diagram for 4, 5 in the arrangement that it's at right now. Okay. And then you're going to notice on 4, 5, it tells you, okay, you're going to reposition it from the original, and you're going to reposition this crank that it's going to go in a counterclockwise direction, 90 degrees from where it's at. And all they want to know is determine the resulting displacement of that piston. So you're going to draw it here. This is going to be like your base position. And then you're going to rotate this counterclockwise 90 degrees from where it's at. Don't put it straight up. Okay, at 90 degrees. It's 90 degrees from where it's at. And now you're then going to find, okay, how far did it slide back? Just that difference. That's problem number 4, 5. Notice that this is also the problem for the displacement diagram, right? Okay. So the same diagram you're starting with. Then what you're going to do is you're going to copy and paste that original diagram. And for 4-6, you're now going to take this very same diagram and you're going to position your crank clockwise 120 degrees from where it's at right now. And you're also going to then determine the resulting displacement of that piston from that original position. Okay. So no new diagram here. You're just going to do that once for these two problems, move it in the new positions, but yeah. Okay. And then how you show it, like I said, your new position, you can do line type, you can do color, you get to choose that. All right. Okay, good. Turning the page, we're going to go to 4-7 and 4-8. Those two go together. Same diagram here. This is also the diagram you're using for the offset slider crank displacement diagram. Okay, so this one you're going to be doing here. This time you're going to have it in this position. You're getting all of the dimensions this time. And then what you're going to do is you're going to reposition the length or the crank. So you are going to rotate it 100 degrees from where it's at in a clockwise direction. So here it's at right now, you're going to rotate at 100 degrees. And then you're going to find out, okay, from this base position, where did that slider or that blade go? Okay, up, down, left, right. Okay. Number 8, this one's kind of neat. This time you're going to take this very same diagram where it's at, but now you're going to reposition it so that your blade is going to be lower by 0.2. So we're kind of going opposite, if you will. You're going to pull the blade down 0.2 from this position, and then you're going to see, okay, what's the resulting angular displacement for that crank? So opposite direction. Okay. And then the third one that you're going to be doing is going to be this rock crushing mechanism. And that's going to be 13 and 14. So you're going to draw it in its original position here. But this time, because it's a crank rocker, you're going to be determining what the angular displacement is for each one of these. Okay. So this is its original position. You're going to find the new position and you're going to be getting the angular displacement, not a distance. Okay. Sometimes students will put a distance at the end there. No. We want the angle that's between that's resulting. Okay. You're going to add that using AutoCAD. And then same thing for 14. And it's going to be utilizing that very same diagram. Okay. Not done yet. Turning the page. Limiting positions. So number 56 here. This is doing the limiting positions and determining the stroke for that very first piston arrangement of 4-5. So you're going back to that first diagram that you make in here. And now you're going to be figuring out how far is it going to go out? How close is it going to go out? And the difference between those two is going to be our stroke, limiting positions. You're going to do the very same thing for the vertical blade going up and down, the offset slider crank. And then you're going to do the same thing, but this time angular displacement on the rock crusher mechanism. Okay. And then we already talked about the displacement diagrams. Okay. So really 3 different diagrams that you're going to be kind of moving around and finding, different values for. Okay. Utilize the AutoCAD. Okay. So for instance, when you're looking at, the 2 versions here of this, you're going to have the original position for 4-5, and then you're going to move it, but then you're going to have that same original position for 4-6. Copy, paste, okay, for the new one. And do that for each one of these, okay? Graphical solutions, and then like I said, on the Excel, if you want to use, using the Excel for the one for sure, because I'm giving you that one, but if you find that offset one and you have it available, check your answers for it, okay? Check your answers. All right. Any questions? Now, that's all that I have. Do you guys feel good about that? Okay. Then I'm going to stop the recording here. Don't leave yet.